Washington just made a definitive decision regarding one of the most critical global supply chains. I mean, the lowest available market price is now officially considered, well, too low.
Right.
In August 2026, the United States established a minimum import price program for polysilicon and its derivatives.
And they layered on a 15% tariff for downstream derivative products on top of that.
Yes, and simultaneously, they authorized a suite of targeted incentives aimed strictly at making domestic investment commercially viable again.
Mm.
We are looking at a fundamental fracture in global trade here.
Because we are watching two entirely different policy systems arrive at the exact same uncomfortable conclusion.
Right, because right now, India is approaching this exact industrial problem from another direction. They are preparing incentives to push their domestic manufacturing base deeper into upstream polysilicon.
Which brings us to a scenario where low prices can be economically efficient for the consumer while simultaneously being strategically destructive to the nation.
And that is the core tension for anyone tracking capital allocation in heavy industry right now. If you are a buyer, you only see today's spot price.
You look at the invoice, you see cheap feedstock, and your margins improve.
Exactly.
But a government, specifically one that is attempting to mandate long-term industrial resilience, well, they have to consider a much longer time horizon.
They have to ask who will actually finance the replacement factory when the current one degrades.
Or when that cheap foreign supply is suddenly cut off.
Let's look at the baseline data from 2024 to understand the scale of this concentration. We really have to look at these statistics carefully. China built enormous scale across the entire solar manufacturing chain.
Right.
In that 2024 baseline, China accounted for roughly 90% of global capacity in upstream solar wafers and polysilicon.
90%. That is a staggering dominance.
It is. Now, contrast that with the United States. The U.S. share of global polysilicon production capacity fell from roughly half in 2005 all the way down to less than 2% by 2024.
Well, let me push back on the premise here and play devil's advocate for a second. If China is building 90% of this material and they are driving down the cost of solar equipment globally, why is that a structural problem?
Because consumers benefited.
Right. Consumers benefited. Project developers benefited. Electricity systems could install significantly more generation for the exact same amount of capital. I mean, if you or I are paying utility bills, we just want the cheapest power possible.
I mean, from a purely static, short-term economic perspective, sure, you were entirely correct. The cheap Chinese imports were not economically bad in a vacuum. They single-handedly drove global solar deployment.
And they systematically lowered capital costs for renewable energy.
Exactly. But we are looking at a temporal trap here. Consumers and project developers are optimizing for today's returns. Capital investment in heavy industry, however, must survive tomorrow's market conditions.
The very input price that improves a solar project's internal rate of return effectively destroys the return profile for any domestic second-source factory.
Low prices expand demand, while simultaneously shrinking supply diversity.
Because when imported material is consistently available below the price required to justify a competing domestic plant, private investors receive a definitive signal: do not build the plant.
Which means the traditional objective of free trade has permanently fractured from the emerging objective of industrial resilience.
Free trade asks a very simple question, which is who can manufacture this product most efficiently?
Right, and industrial resilience asks a completely different question. Who can still manufacture this product when the cheapest supplier is suddenly unavailable?
Those two questions produce conflicting answers. And if you are trying to understand the long-term viability of these supply chains, you have to transition from the abstract goals of government policy directly to the balance sheets of project finance.
We have to evaluate this using the first durable framework required for this shift, which is market price versus replacement cost. Market price simply answers what you can buy this material for today,
while replacement cost asks at what price somebody will actually agree to finance, construct, and maintain the next competitive unit of capacity.
The engineering and operational reality here is severe. If the market price stays below the cost to finance and operate a new facility, the factory is never built. Existing high-cost producers in the West are forced to close. Expansion plans get canceled.
And the damage compounds beyond just the physical infrastructure.
Absolutely. The specialized engineering talent disperses to other industries. Supplier relationships weaken, and the underlying equipment orders disappear entirely.
We have to ground that reality strictly in capital markets. A project finance lender does not finance resilience as an abstract public good. They finance expected cash flow.
Right.
If global prices remain below a domestic plant's sustainable economics for years, that factory might be highly desirable to a policymaker concerned with national security, but it is utterly unbankable to a private lender.
Because project finance will not naturally build these factories under current market conditions, we must look at how governments are attempting to force the economics to work. This requires a clear distinction between the actual policy tools being deployed.
Let's look at the mechanics.
There is a structural difference between a percentage tariff and a minimum import price. A percentage tariff simply moves with the underlying price of the good.
Right.
If the foreign manufacturer's price collapses far enough due to oversupply, the tariff-adjusted import price can still fall below the survival threshold of the domestic producer.
A minimum import price, however, creates a credible floor during periods of global oversupply. It mandates a hard stop on how cheap the input can become.
That distinction is critical when you are evaluating capital expenditure risks. Look at the current market dynamics. Manufacturers have currently built far more polysilicon capacity than the global market actually needs.
Spot prices fall, margins disappear, and the lowest-cost producers keep competing aggressively for volume.
Under those conditions, building a new factory in a higher-cost jurisdiction like the U.S. or India looks impossible to finance. A price floor is designed to change that specific downside case.
But it introduces a major capex risk, which is policy duration versus asset duration. Let's expand on that duration mismatch because it is the linchpin of the financing model.
Sure. A heavy industrial factory takes years to permit, construct, and ramp up to full commercial production. Its economic life must stretch for decades to justify the massive initial capital investment.
A tariff or a price floor, however, can vanish in a single election, a sudden court challenge, or a shift in bilateral trade negotiations.
Which means a weakly credible policy might create a short-term rally in domestic manufacturing stocks, but it will not produce actual steel in the ground. Private capital requires strict confidence in the rules governing future cash flows.
That is why we are seeing industrial policy operate through multiple balance sheet channels simultaneously. Let us detail exactly how these specific tools make strategic capacity investable.
Capital grants are used up front to directly reduce the initial construction cost. Tax incentives are deployed to improve the ongoing unit economics per ton produced. Government-backed financing lowers the weighted average cost of capital.
For anyone modeling this out, well, if a private bank demands a 12% interest rate because of the structural risks we just discussed, the project is dead.
Right.
But if a government steps in with loan guarantees, bringing that cost of capital down to 5%, the math on the spreadsheet suddenly turns positive.
Then, price floors limit the downside revenue risk. Long-term offtake agreements create demand visibility so the factory knows it has a buyer, and domestic content rules attempt to manufacture a captive market.
Financially, all those mechanisms are attempting to define and fund what we call the resilience premium. Think of this resilience premium like an institutional insurance policy on an underlying asset.
Right. If the globally cheapest supply chain is highly concentrated, diversification acts as your insurance.
But insurance requires a premium to be paid continuously. If the supply chain functions perfectly, that premium feels like deadweight loss dragging on your margins.
But if a geopolitical event fragments the market, that premium is the only mechanism preventing total operational failure. We have to track that resilience premium downstream through the exact invoice path to see who actually pays for it.
Let us trace that path. If a government successfully protects the upstream polysilicon producer with these price floors, the domestic wafer manufacturer immediately pays more for their feedstock.
If you then protect the wafers, the cell manufacturers face higher input costs.
Protect the cells, and the module manufacturers lose a piece of their global cost advantage. Eventually, the solar project developer receives the final inflated invoice.
This creates a severe distributional conflict inside the domestic industry itself. You have a supply chain at war with its own margins.
The upstream producer requires a higher protected price simply to survive, but the downstream manufacturer requires the cheapest input available to maintain their margins against foreign competition.
The project developer wants cheaper modules to improve their project returns, and the utility just wants reliable power at a low capital cost.
The government is attempting to satisfy all these conflicting objectives: domestic employment, supply security, and rapid renewable deployment simultaneously.
Those objectives do not fit neatly into a single financial model. The critical pass-through question remains for anyone analyzing these markets. Who ultimately absorbs the resilience premium?
Does it appear in public spending through endless government subsidies? Does it compress the manufacturer's profit margins?
Or does it increase the capital cost of the final solar project?
Or does it ultimately reach the final electricity consumer in the form of higher utility bills?
That brings us to the physical reality of building these assets. We need to shift from the financial protection of a single asset to the massive operational challenge of building an industrial network.
China's cost advantage requires more precision than simply citing cheap labor. Polysilicon and solar manufacturing are highly complex industrial systems. They rely heavily on cluster economics.
We need to define what a cluster actually looks like in practice. It is not just about having a few factories in the same geographic region.
Electricity costs, plant utilization rates, supplier density, equipment productivity, logistics, and process learning all compound upon one another.
If a specialized piece of equipment breaks down in a highly dense cluster, the original equipment manufacturer likely has engineers within a 10-mile radius who can be on the floor in an hour.
Furthermore, a manufacturer embedded inside that dense industrial cluster can solve engineering problems collaboratively, faster, and spread fixed costs over a significantly greater output.
Building one subsidized factory in a new jurisdiction does not recreate the economics of that established cluster, which is why factory localization is not supply chain localization.
A factory is a single physical asset. A supply chain is a living network.
Right.
Networks require qualified vendors, localized engineering knowledge, specialized transportation, strategic inventory, and most importantly, enough aggregate demand for each tier of suppliers to survive independently.
We see this exact network deficit in India's current strategy. Look at their sequence of capital deployment. They have aggressively expanded module and cell assembly.
Assembly capacity can scale rapidly because it is closer to the end consumer.
But they are now facing the vastly more difficult task of integrating upstream into ingots, wafers, and the polysilicon itself. The industrial ecosystem required to feed those downstream plants cannot be built overnight.
A government can issue a press release celebrating a new domestic module plant. But if that plant requires imported cells to operate, the structural dependency remains entirely intact.
Build the cell factory, and it relies on imported wafers.
Build the wafer plant, and it remains completely dependent on imported polysilicon. The vulnerability just shifts one node further up the chain.
We also have to introduce a critical engineering distinction here, specifically regarding the difference between solar manufacturing and semiconductor manufacturing. High-purity silicon matters immensely to both.
But solar-grade polysilicon and electronic-grade polysilicon are not interchangeable products. Electronic-grade material requires significantly tighter impurity controls and an entirely different, incredibly rigorous qualification chain.
Building domestic solar polysilicon capacity does not automatically secure the specific silicon required for advanced semiconductors.
This is where broad policy often fails the technical reality. Policymakers must define the actual bottleneck. Stating a goal of polysilicon independence is economically vague.
Which grade of material are you securing? Which specific chemical process? What purity level? What qualification standards are required by the end user?
A country can spend billions of dollars achieving absolute security in solar-grade material while remaining completely exposed and dependent on foreign electronic-grade feedstocks.
Strategic resilience must be engineered around specific industrial requirements, not merely announced as a broad category objective.
That raises the macro challenge regarding the ultimate endpoint of these policies. Total self-sufficiency is uneconomical. The capital expenditure required to replicate an entire supply chain domestically is prohibitive.
The goal should instead be framed as industrial portfolio construction. The objective is not to reach zero imports. The objective is avoiding a single failure point capable of halting the entire supply chain.
A resilient system likely requires multiple qualified external suppliers, strategic domestic inventory, a baseline of local capacity, and the technical ability to expand production rapidly during a geopolitical disruption.
To evaluate whether that localized capacity can actually survive, we have to stress test these assets against the 5 horizon risks that will dictate market dynamics over the coming decades.
Let's systematically walk through these 5 variables from the data. First, energy.
Right, polysilicon production is extraordinarily energy intensive. We are talking about the massive thermal and electrical input required to reduce quartz to ultra-pure silicon.
A country attempting to localize production without access to fundamentally competitive industrial-scale power will permanently handicap its own cost structure. Trade policy cannot indefinitely subsidize an expensive electron.
Second, financing. We return to the cost of capital. High interest rates alter the return a new factory must earn just to break even.
Industrial competitiveness is directly tied to the macroeconomic interest rate environment.
Third, currency fluctuations. Trade protection always operates inside a moving foreign exchange environment.
A weaker domestic currency makes imported processing equipment and raw feedstock more expensive, while shifting the relative competitiveness of local exports.
Fourth, technology substitution. This is the engineering risk. If module manufacturers transition to a completely different photovoltaic architecture, or if they simply engineer thinner wafers that require 20% less silicon per watt, the fundamental demand curve for polysilicon shifts.
You might have just spent $2 billion building a chemical plant based on a volume assumption that the technology itself renders obsolete before you even finish construction.
The strategic value of a specific facility can degrade rapidly based on downstream innovation.
The fifth horizon risk is provenance, and this fundamentally alters global trade mechanics. Supply security is now about far more than geography.
Customers and regulators demand exhaustive evidence detailing exactly where materials were processed, the carbon intensity of the electricity used at that specific facility, the origin of intermediate inputs, and strict local content compliance.
Price is now just one dimension of trade. The absolute cheapest ton of polysilicon on the market is commercially useless if it lacks the documentation making it admissible in the target market.
Documentation, origin data, and financing eligibility are now embedded into the product itself.
But protecting these industries introduces the greatest political and capital risk of all, which is the lock-in trap. Temporary industrial protection has a strong, proven tendency to acquire permanent constituencies.
Let's trace how that lock-in actually occurs on the ground. Once a factory is built, it employs hundreds of local workers. Regional banks hold the underlying loans.
Local municipal governments become structurally dependent on the tax revenue generated by the facility. Surrounding suppliers invest their own capital based on that primary facility's continued operation.
Once abstract capital becomes physical infrastructure, reversing the protective policy becomes economically and politically painful.
You might introduce protection today because the supply chain is globally concentrated. But a decade from now, you might maintain that exact same protection simply because domestic capital has become entirely dependent on it to survive.
Therefore, successful industrial policy requires strict, objective performance metrics to ensure it is protecting evolving capability, rather than merely sustaining uncompetitive, stagnant capacity.
We have to measure cost reduction over time. We have to measure yield improvements, plant utilization rates, the rate of private capital participation, and eventually the ultimate test, export competitiveness.
Does the protected industry actually develop local suppliers? Does it reinvest its protected profits into research and development? Can it eventually earn export customers who are not legally forced by their government to buy from it?
If those indicators remain stagnant, the resilience premium we discussed earlier devolves into a permanent wealth transfer from the taxpayer and the consumer directly to an inefficient asset.
We must also consider the dominant incumbents calculus in all of this. China is not static within this shifting system.
Persistent oversupply and very low prices preserve global customer demand, but they also destroy domestic profit margins within China. This triggers inevitable industry consolidation.
The rational response for Chinese producers is to evaluate their own capital allocation problem. Do they keep expanding capacity at a loss to defend their global cost leadership, or do they consolidate enough capacity to restore sustainable returns?
Furthermore, trade barriers do not eliminate competition, they simply redirect it.
If a protected Western or Indian market becomes valuable enough, the rational response for foreign producers is to utilize their engineering advantage and manufacture directly inside that protected jurisdiction, provided ownership structures and local content rules permit it.
That frames the ultimate capital flow problem for the next decade. A country might successfully win the local factory jobs, and some Tier 2 suppliers might become local.
But the core technology, the operating profits, the advanced equipment design, and the strategic decision-making remain abroad.
The metric for trade is no longer simply where a product undergoes final assembly. The metric is how much value added actually became local. Winning the factory does not mean winning the company.
And this exact dynamic applies far beyond polysilicon. The data shows we are seeing the identical framework applied to battery manufacturing, semiconductor fabrication, active pharmaceutical ingredients, and the processing of critical minerals.
Any sector where the cheapest global producer becomes sufficiently dominant eventually faces the same structural argument regarding absolute efficiency versus necessary redundancy.
The West is not abandoning free trade. It is fundamentally changing the objective function of its economic model. Traditional trade policy placed almost exclusive weight on geographic specialization and immediate consumer welfare.
The emerging model is attempting to mathematically price variables that markets historically price imperfectly. We are now pricing in concentration risk. We are pricing in surge capacity, supplier reliability, and the sheer option value of maintaining a functioning second source.
The ultimate test that will survive any administration and any single technology cycle is whether an economy can successfully finance a second source without destroying the economics of the downstream industry that consumes it. If you want the unlayered global to follow the next layer of this industrial shift, tell us which trade-off deserves more attention, the hidden cost of dependence or the hidden cost of independence.